Thanks. Let me count. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, everybody's here. So I started to talk about visualization yesterday, but didn't have quite enough time or energy to really do it justice. So let's talk about that again. It's the problem of visualizing. Solutions. And I suppose really I'm more talking about not just one solution, but sort of how to look at the differential equation as it's really connected to a vector field in the plane, actually. So in particular, if we think about, let's see here, m dx plus n dy equals to 0, right? Suppose that this is the differential equation we're thinking about. And, if we divide by dt, this gives us what? M dx dt plus n dy dt is equal to 0. Or you could look at this as m comma n dot dx dt dy dt equals to 0. So what I'm trying to say is if, let's say, r of t equals to x of t, y of t, parameterizes the solution to, let's give it a name, star. So, and just for the sake of discussion, let's assume this is an exact equation. That's the easiest to discuss. And if we believe Pfaff's theorem, that's not really a loss of generality. So here's star, right? So what does it mean, a parameterization of this? What's the solution to star? The solution to star would be something like f of x comma y equals to a constant, right? That's a level curve. What does it mean to parameterize a level curve? It means that if we plug in the parameterization of it, right, we'd have f of r of t equal to what? Like the constant, right? I mean, that's what it means to parameterize a solution. I give you a function of x. X is a function of time. Y is a function of time. When I plug those functions of time into the level curve, which is the solution to the differential equation, it works, right? So geometrically, what's the relation between a parameterization to the solution and these coefficients m and n? What does this say? The dot product of this and that is 0, right? What does it say about the relation between, say, this vector field, mn, and this tangent vector, dx dt, dy dt? They're what? Really? Who's up on the roof? Who on earth would want to be up on the roof right now? I mean, it is beastly out there. They're perpendicular, right? So let's see here. Maybe if I give you an example, this would be less ethereal. How about this? X dx plus y dy equals to 0. This is really the differential of 1/2 x squared plus 1/2 y squared equals to 0. So the solution in terms of level curves is what? It's 1/2 x squared plus 1/2 y squared equals to a constant, right? AKA x squared plus y squared equals to r squared, right? What's the vector field here? Mn is what? X comma y, right? Can you visualize that vector field? I mean, there's not many I can draw without a lot of effort, but this is one of them. So like this vector field, let me give it a name and call it f. Right? What's it look like? I'll do the easier thing. What do these look like? Circles, right? So the vector field, what's it look like? It's perpendicular to that. We believe the calculus. But we also, what is this? This is the position vector to the point, right? So it's just radially outward, you know? And of course, these vectors get longer if you want to indicate magnitude by distance. I'm not sure I do because that picture gets really awful really fast, but yeah. So these, you know, I don't know, it's hard to draw a lot of them. What's probably better is to draw what are called streamlines to the vector field, right? This dotted line here would be a streamline to the vector field F. What's a streamline to the vector field? For shame we don't spend more time on this in Calculus 3, by the way. A streamline to a vector field is a curve that lines up with the vector field. Basically, it takes the direction of the vector field as its tangent field. So the tangent vector field to this is what? It's, if this is going this way, the tangent vector field, it's like this, right? The tangent vectors point like that. Well, that's also this vector field in terms of direction. So lines from the origin are streamlines of the vector field, right? So let's see here, what's going on? These are solutions to the differential equation, the red circles, right? And these, seems relevant to current Hollywood productions. Let's see here. These are the streamlines to the vector field. These are this is a set of trajectories, right? The red circles are, these trajectories are the solutions to the differential equations. The blue lines to the origin are streamlines to the vector field. They're also, what's the relation between the blue and the red lines? These have a name. These kinds of families of curves are called orthogonal trajectories. So I mean, there's a lot to see here in terms of the relation between things. Let me just, boil it down for you, something, just a takeaway message here. If you want to ask the question, what does this differential equation look like, right? What are the solutions look like to this? There are going to be the set of curves which are perpendicular, locally perpendicular to Mn, right? Now, how could you say it more directly? You can either look at this, solutions are perpendicular to streamlines of Mn, right? And if you look at this, you really could go plus or minus that, couldn't you? Because there's really no sense of direction. I could just as well put minus m minus n, I'd still have 0, right? If A is perpendicular to B, minus A is also perpendicular to B. That's how vectors work, right? But can we say something more direct rather than just saying the solutions are perpendicular to the streamlines? What do the solutions line up with? How about the solutions are streamlines of what vector field? Plus or minus what vector field? In 2 dimensions, this is easy. How do you find a vector field which is perpendicular to a given one? I give you the vector 3, 4. How do you find the perpendicular vector? Rotate it 90 degrees, right? But in terms of algebra, you just flip the 3 and the 4 and put a minus on one of them, right? 3, 4 is perpendicular to minus 4, 3. Or 4 minus 3. So plus or minus, just flip the letters like that. All right? Now this streamline condition, what does it say directly? Let's just think about that for a second here. Streamlines, what's that mean? to mn has, right, dr dt equal to m, let me call this thing f, has dr dt equal to f of r of t. In other words, the tangent to the streamline matches the vector field at each point you consider. Let me write that in terms of mn notation. In other words, dx dt, dy dt, right, is equal to m comma n. All right? This is two differential equations, right, written as a vector. We can rewrite this as two differential equations. Let me just do that. This we can trade for dx dt equal to m and dy dt equal to n. So to find a streamline to a vector field, all right? Assuming the vector field doesn't have a time dependence, all right? We're talking about static vector fields. But if I want to find the streamline to a vector field, I have to solve this system of differential equations like that. All right? So that's what this tool p-plane is actually geared up to do. It just plots the direction field for these guys. All right? So let's see here. We just worked through this. We want to find, so if we want to plot solutions to this, right? I should look for streamlines to what? I should think, okay, so my m, so I want to look at what? Like, say y minus x, something like that, right? To look at, so I would look for dy, dx dt equal to y and dy dt equal to minus x. This solutions to this should be streamlines to the vector field y comma minus x, which in turn should be solutions to the x dx plus y dy differential equation. So let's, and here this tool, you see what I'm doing? X prime equals to what was it? Y? Y prime equal to what? Was it minus x? Is that right? And that looks good. Graph the phase plane. Check it out. And if you click on here, it'll generate solutions numerically. As you can see, there's our circles, right? See that? What happens if instead of doing y minus x, if I do x, y, what would you expect there? What should this be? Then we're looking at streamlines to the vector field x, y. Right? These should be lines from the origin because they line up with the vector field x, y. And of course, these will not be solutions to the differential equation. These will be orthogonal trajectories to that differential equation x dx plus y dy. All right? Just like that. What if we tried something else? What did we solve earlier today? What was that thing we solved? What was it? Dy dx equal to what was it? Was it x plus y minus 6 squared? It's kind of scary. Let's see here. So this would be what? This would be x plus y minus 6 squared dx minus dy equal to 0. So let's try that, see what happens. So I should do, what would this mean if I should put a 1 here, right? And I should put a x plus y minus 6. I don't know if it's going to be smart enough to do that, though. Looks like it was. we had what, like tangent, what was it? The solution had a tangent in it, didn't it? I think you can see that. See what I did was I identified that m is equal to this and y is equal to -1. So I plotted, for the phase plane, I looked at dx dt equal to 1 and dy dt equal to x plus y minus 6 if I haven't made us silly. So these should be streamlines to what? Solutions are streamlines to, 1 x plus y minus 6 quantity squared. Yeah. All right. Anyway, I don't think there are good homework problems about this. I'll probably make you up a problem or two on the quiz about this. And you can either use p-plane. I'll probably ask you to visualize some differential equations using this tool. But you can use p-plane in MATLAB if you don't like this website. I sent you a link to the website. So to use the website, it's pretty self-explanatory. You can just do like screen capture and print screen for your report, right? Or you can print it out, Or if you're really a glutton for punishment, I guess you could get some like tracing paper and put it over your screen and but I don't really recommend that. I think screen capture is probably the way to go. I don't know if you really want to print this lovely blue. I don't know. Maybe cut this piece out to not kill your printer. I don't know. Like, I'm using the school printer. I don't care. They're fine. Fair enough. It's 10 cents a copy either way, right? Whatever. How much is it for you guys? I used to be able to print a set of like 400 pages of notes for like $11 here. Yeah, that went away. All right. Enough about this. Let me put this away. So I hope that gives you a better sense of how we can visualize. I mean, it's a natural question to ask, right? Basically, the question I was asking in this and trying to explain to you is geometrically, the solutions are sort of perpendicular to the streamlines of the vector field Mn. That's all I'm really saying, right? So if you want to visualize the differential equation, you got to think about orthogonal trajectories a little bit to understand this interplay that I've explained. Hopefully I've explained. All right. Okay, well, that said, so there's one obvious application to differential equations is we can study streamlines to two-dimensional vector fields, right? There are other things we can do, which is just to find orthogonal trajectories, right? So example, I guess this is example, I don't know what example, example 6, oh, thank you. So how about this? If x squared minus y squared equals to 1, then find the orthogonal trajectories. And let's trade this 1 for a constant k. Trajectories to this family of curves. All right? So how do you do such a thing? Well, here's one way. I can just be like, okay, so 2x minus 2y dy dx is equal to 0 for the given curve, right? So we can solve for dy dx. What's dy dx equal to? Right? Right? Now, if I solve that, I'll get back where I started, right? This family of hyperbolas, But if I want to find orthogonal trajectories, how's that work? We usually start abbreviating it OT because, well, orthogonal trajectories, not exactly fun to keep writing. So we would want to solve dy dx equal to what? Draw a picture of it, right? I mean, if this is the point in the original curve, this has slope dy dx, right, at this point, xy. So the orthogonal trajectory is something like this, right? And so it has slope So, I mean, there's two different dy dx's going on here. You have to be careful, right? There's the dy dx of the orthogonal trajectory, which is what we're trying to find. There's dy dx for the given curve, which is given, right? So to find the orthogonal trajectory, I don't solve dy dx equal to x over y. I solve dy dx equal to what? Well, minus 1 over x over y, right? Also known as minus y over x. What I'm showing you right now is the calculus 2 way of thinking, all right? Which is not wrong, and my other way of thinking is not much more efficient. So, I mean, there's just, you can either think of this as I'm doing right now, or we can use differentials. Let me finish our current treatment. So this gives me what? This is dy over y equals to minus dx over x, right? Which gives me what? Well, integrate both sides. Natural log absolute value of y equals to minus the natural log the absolute value of x plus a constant. And I'd like to, so you know, this gives me the natural log the absolute value of y equals to the natural log of 1 over the absolute value of x plus a constant, right? Bringing the minus inside to make the argument reciprocal. And so then what? I can solve for y, right? So this gives me the absolute value of y is equal to e to the natural log of 1 over the absolute value of x plus c, right? Which is e to the c times 1 over the absolute value of x, right? Fine, let me put another algebra step down here. E to the natural log of 1 over the absolute value of x. Sorry, I put the c first, but you can commute these, right? Anyway, this is e to the c over the absolute value of x. And if that was all equal to absolute value of y. So finally, we get y is equal to some constant, let's say k divided by x, right? Because I get a plus or minus e to the c, right? Which could be either, you know, negative or probably y equals 0 here appears as an exceptional solution as well, right? Now, if I hadn't put away the projector, we could look at the direction field corresponding to the differential equation, right? And we could see this. We can actually see these solutions if we run through the correspondence I just went through here. I'll just draw a picture. So depending on whether k is positive or negative, you either get hyperbolas which do what? Open sideways or vertically, right? So this is the given family of curves looks something like this, right? So these are the x squared minus y squared equals to k. There's also the asymptotes, right? In fact, the asymptotes are what? These are just what? The case k equals 0, right? K equals 0 gives us the asymptotes. Those are the dividing line between k positive and negative. And then what do the orthogonal trajectories to the given family look like? Well, I'll draw those in red this time. Those are these functions, right? These are also hyperbolas, but rotated 45 degrees. And they take the xy axis as their asymptotes. Oops, that was dumb. Let's see here. So somehow I should have seen x equals to 0 and y equals to 0. I guess, again, it's this thing I was talking about last time, using dy dx. Maybe it's better to look at this instead as, ooh, I really messed up this marker. Sorry, dy, oh man, look at that, what a mess. Minus y over x dx. So we could really look at this as x dy plus y dx equal to 0, you know? So if you look at it like that, it becomes fairly obvious that either x identically equal to 0 or y identically equal to 0. These both solve the differential equation when you think of it in Pfaffian form. And geometrically, it becomes clear I should see those in the family, right? Those are the asymptotes to the other, these guys, which look like this. So to get the full story, we have to think about the Pfaffian form as opposed to these rather limited dy dx way of thinking. Yeah, but anyway, if I had done my picture careful, these shouldn't merge. We have unique existence and uniqueness. Like there's a unique solution through each point. Okay, there's only one point where solutions meet. The origin, right? The origin is this point where we have many solutions meeting. But any other point, there's a unique solution in each one of these families of curves which goes through it, right? Just one, either line or hyperbola. And those are orthogonal trajectories. Okay, so what's the point here? How do you find the orthogonal trajectories to a given family of curves? Find dy dx, right? And then solve dy dx equals to minus 1 over that, whatever that is. Can you guys tell me how would this be different if we used the differential notation? So here I'll do example 7, same example, but in my other way of thinking. X squared minus y squared equals to k. Find OT. So the other way of doing this would be 2x dx minus 2y dy equals to 0. That's the differential equation which that family of curves solves, right? So if I want something that's perpendicular to that, I just flip and add a sign. It gives OTs. And if we're lucky, that'll be exact. Is this exact? Well, let's see here. What's partial m, partial y is partial y of what? 2y, which is 2. What's partial m, partial n, as in nanu, partial x is partial x of what? 2x, right? And that's 2. Hey, it's exact. What's the level function? We can rewrite the orthogonal trajectory differential equation as the differential of what level function equal to 0? that would, if I did x squared y squared, right? I mean, I appreciate the guess, but that would give me 2xy squared dx plus 2x squared y dy, right? So that's not going to do it. Yeah, 2xy. Now you can either get that from guessing or from doing the integral like we did yesterday, yeah? So once you see that this differential equation is just that, the solution is 2xy equals to some constant. I'll call it c tilde. So in other words, y is equal to c tilde over 2x, aka k over x, yeah? Which is what we found the other way as well. So which is better? I mean, thinking about differentials and using the perpendicular idea to swap the m and n in a sign, or doing the negative reciprocal of dy dx. I mean, I don't care. You do whatever you like, but you do need to know how to find orthogonal trajectories to a given set of curves, right? Make it clear in your mind the method you're going to use. So many students lose points in this, and it's needless. It's needless. Because it's not a hard problem. It really isn't. All right, let us move on. I've got about 20 different applications in the notes. I think I'll cover about 3 of them in class, and then we'll just look at the rest with the projector, because otherwise I'll go nuts. Let's talk about physics for a little bit, yeah? Really just motion for the most part at the moment. So the basic story is, and really just one-dimensional, all right? So in short, we have this. We have mass times acceleration is equal to the net force, right? And in one dimension, that pretty much does it. So if we, let's say that x is the position, and we'll say v is dx dt, also known as x dot, right? Acceleration is dv dt, also known as v dot, or x double dot. These are fun classic notations for time derivatives from physics, all right? What does it mean for the force to be conservative? Or let's just say F. The net force doesn't have to be conservative. We could just have a force. F is conservative. What's that mean? It means it's minus du dx for u equal to the potential energy function, right? So let me give you a quick derivation of kinetic energy at the level of differential equations, okay? So if we have the net force, suppose that the net force is conservative, all right? What's that give us then? We have ma equals to minus du dx, right? But it's a good exercise to rewrite this as, say, m dv dt plus du dx equal to 0. And here's a trick that's a well-known trick from physics, is you take Newton's equation and you multiply by velocity, all right? So we're going to multiply by m dx dt dv dt plus dx dt times du dx, right? Now, this is going to give us ddt of 1/2 m v squared plus u. See, because this right here is really just du dt by the chain rule, right? And, you know, it's a simple exercise of the chain rule again to derive. I mean, here, let me just pick on that for a second. What's ddt of 1/2 mv squared 1 half, m is constant, right? So we get 2v times dv dt, which is what? The 2's cancel. We get m, we get v, we get dv dt, which is what? I mean, that's exactly what we have here, right? Because dx dt is v. So you see, this is, of course, what? This is Newton's second law, right? F equals ma, yeah? And you can see that Newton's second law implies what? It implies that this quantity, the time derivative of it, is equal to 0. But what is this quantity? You guys leave me out to dry here. Let's see. This is energy, right? So this is the kinetic energy, yeah? And this over here is the potential energy. So what we have is that if the net force is conservative, the sum of kinetic and potential energy is conserved. It's a constant. I wanted to share this derivation with you, though, because it's at the level of differential equations. What you saw in your class probably wasn't this, right? We probably did some sort of integral derivation or something. All right, so that's just a derivation I share with you. We'll come back to that eventually later when we study energy analysis in the phase plane. But that later in the course, we'll get back to that discussion. Now, so what was the thing you couldn't do in Physics 231 here? What was the one thing we describe it qualitatively? Friction, right? But our friction was kind of boring, right? We did stuff like push something along a table, and you could either look at its kinetic friction or its what? Static friction, right? But did we do something like, well, the friction force depends on the velocity, so find the equation of motions? Like that never happened in Physics 231, right? We did not look at velocity-dependent friction forces, did we? Why didn't we do that? Is there a reason? So we didn't have the math is the reason, all right? So now we do, so we can. So let's look at one of those. So here, we'll look at MA equal to, let's see here, just to get started, minus BV, where B is greater than 0 and V is velocity, all right? Again, we're thinking about one-dimensional motion. So this is very much not a conservative problem, right? I mean, energy is not going to be constant in this problem at all. The net force, is the net force a function of position? Can we write it as the derivative of some potential energy function? No. It's not the case, all right? In fact, if you go through the same derivation we just did over there for this one, what would you derive? Here the energy is just, well, all right, you know what? We should allow time for that, so let me do that. By the way, the energy here is what? It's 1/2 mv squared. This won't help us solve the problem, but maybe it'll give you some intuition for what we're doing. The energy is 1/2 mv squared. There is no potential energy in this problem, right? If I take the differential equation that we're looking at and I multiply by velocity, what does it give me? It gives me mv dv dt equals to minus bv squared. Through the same math I just did, this says that the derivative with respect to time of 1/2 mv squared equal to what? Minus bv squared. In other words, dE dt equals to minus bv squared. So there you go. Energy not conserved. In fact, the energy does what? It decreases proportional to the square of the velocity and the given coefficient of friction, b. Although that's not the coefficient of friction you had in 231, right? I'm just saying it's some coefficient which describes friction. The actual way friction works for a car or something like that is actually way more complicated. It's something more like this, guys. It's something more like the force of friction is like there's some constant m, and it's v to the like b. Well, maybe I should say n. But this n is function of v. So like, it's something more awful what real friction is for an actual something you're interested in, because it behaves differently at different velocities. So I think it's something like at low speeds, the velocity for a car might be, depending on the profile and stuff, might be dependent on like the square of the velocity. But when you get to a higher speed, it might be dependent on like the cube of the velocity. And there's some kind of interpolation between those two regimes. So it's really quite awful, the real story for friction. But so what we do is we still kind of cheat and just look at something more simple that we can deal with. But at least it gives us a better sense of how friction works when there is a velocity dependence. So that's what we're going to do. We're going to solve ma is equal to minus bv. This is a good, more complicated problem than we were able to solve in 231. It's really something new. Energy is not conserved, right? And but I just, as a point of honesty, I should mention to you that the actual formula for the force of friction due to velocity is probably something more complicated for actual interesting physical objects. This would be something that would be true in some particular approximation. All right, so how do we solve this? We got ma. So there's two things I want to find. Our goal. Find velocity as a function of time. That's goal number one. And goal number two, we want to find the velocity as a function of position. Any math majors here? Okay, so don't tell the math majors I wrote this. Very good. But you guys know what I mean by that, even though it is a little bit incorrect, this notation. All right. But whenever you see somebody write like f equals f of x or, g equals g of t, what they're trying to tell you is that f is a function, it's a function of x. G is a function, it's a function of t. This is what this notation means. If you have a math major friend who's overly pedantic, it will blow their mind what you wrote, though, so be careful. But anyway, my secret is safe with you, I guess. So no one's watching this on the internet. So it's safe. It's here. All right. So here we go. M. And so we'll try to write our solutions in terms of the initial position and initial velocity, okay? I don't think we'll need the initial position unless we could also find position as a function of time, right? Maybe we should also do that. There we go. Maybe I should do that actually. Maybe this should be 3, right? And this should be 2. That would probably make more sense. All right. All right, so we've got m dv dt equals to minus bv, right? This is actually really simple, right? dv over v equals to minus b over m dt. So we separated variables. I mean, I don't know. I think the truth told, when I have taught physics in the past, and I haven't for a few years, I probably made students do this in 231 because I'm evil. I mean, because I care. And because really, this is just calculus 2, right? And you should know calculus. Well, I guess you don't have to have calculus 2 before 231. Man, that's why I stopped teaching it. All right, anyway, see here. Natural log, the absolute value of velocity, right? Actually, point of order here. In an applied problem like this, it's really nice to work in initial conditions at this stage in the game. So what I would do is I would integrate from initial velocity to final velocity. and from initial time to final time. Right? If I do that, then rather than having some pesky integration constant I don't care about, I actually have useful physical labels that I like and are really what I'm after long term in terms of a formula. So this is natural log the absolute value of the final velocity minus the natural log the absolute value of the initial velocity equals to minus b over m tf minus t naught, yeah? Now, if you want to make this formula less annoying, we can do what? We can say, okay, so I'm going to set Vf equals to V, and T naught equals to 0, and Tf equals to T. And if I make those rather customary choices, then this is a little bit nicer, right? I get natural log, the absolute value of V rather, equals to the natural log of the absolute value V naught minus BT over M, yeah? And then exponentiate both sides, and what do we get? I suppose technically speaking, you get the absolute value of V is equal to the absolute value of V naught times e to the minus b, bt over m. But if you think about it, the sign of V has to match the sign of V naught, so you can drop the absolute values. Think about how the solution plays out. But there it is. That's the answer to 1. So, there's a lot of different ways I can change this problem ever so slightly. Like, so maybe on your test I don't give you this exactly. I do something like, I don't know, put a 3 here. It's still a problem you can solve, right? It's a good question. So find the velocity in terms of the initial velocity and time. And if I have any common sense, I'll say, assume that, I would say something like, you're given V equals to V naught at t equals to 0. So you want to write your answer in terms of the initial velocity. Yeah. All right. So then how do we do 3? It's 2. Idiot. So we have V is what? It's dx dt. Yeah. And that's equal to V naught e to the minus bt over m. Yeah. So can we solve for x? I think we can, right? This one we just integrate both sides, right? I mean, we get dx is equal to v naught e to the minus bt over m dt. So if we integrate this from, say, x naught to xf, and then we integrate that from, say, t. Well, I guess we've already put t naught equal to 0, so I might as well do from 0 to the final time. The reason I want to do final time, guys, instead of time is because time is an integration variable, so, I shouldn't use t as the fixed but arbitrary time and as the integration variable. So that's why I introduced this t, so the final time. So xf minus x naught from that integral, and over here we get, how do you integrate that? What do you get? What's the integral of e to the minus bt over m? Right, so we get minus m v naught over b e to the minus bt over m, and I'll put an evaluation bar here for good measure, from time 0 to final time, yeah? Let's see here. So that is really mv naught over b minus e to the minus b final time over m. And so setting the final time equals to t to make my formula prettier. We get x of t equals to the initial position plus mv naught over b minus e to the minus bt over m. Yeah. So there you go. That, folks, is the position as a function of time. And I guess I've added, what else have I said? You're also given what? X equals to x naught at time equal to 0. I made that up, didn't I? So sorry about that. And then what? Now we're supposed to find the position, number 3, we're supposed to find the velocity as a function of position. So how could you do that? One way you could do it, don't do this, but one way you could do it is to solve this for time, right? You could solve this for t, and then plug it in down here. Or if you're smarter, you'd solve that for e to the minus bt over m and plug that in down here. That wouldn't be too bad, right? But, you know, when I put a 3 here, or a 7, or a 13, or something else, or I trade this out for the sign of the velocity, or whatever horrible thing I do to you, I mean, for you on the test, you don't want to do the algebra. We want a calculus method to find the velocity as a function of position, right? And that's where the VD/VDX trick comes into play. We already seen it over there. I'm going to show you, use it again here. So here's it. Here, we make the substitution at the level of calculus rather than algebra. So we're solving m dv dt, right, equal to minus bv. But the thing is, we can rewrite this as m dx dt, dv dx. If you just tilt your head and squint, you can see that there's a dx over dx hiding there, right? You see it? Look here really hard, you can see it. As you can see, the x's cancel, right? I mean, this is the chain rule. It's too good to be true. So this is m v dv dx equals to minus bv. Right? And separate, integrate. Oh, the v's cancel. Cool. So this just gives us dv is equal to minus b over m dx. It's almost too stupid. So integrate from v naught to vf. Integrate from x naught to xf. We get vf minus v naught equal to minus b over m. Final position minus initial position. In other words, vf equals to v naught minus b over m times xf minus x naught. Or v as a function of x equals to v naught minus b over m times x minus x naught. There you go. That's the velocity as a function of position. Now, if you're not careful, I always try to point this out. Sometimes it's helpful to look at answers in terms of limiting cases, right? Like what happens as x goes to infinity in our answer for 3? If we're assuming that b and m are positive, right? So x naught is fixed, v naught's fixed, they're finite. What happens to this velocity as x goes to infinity?
Would get smaller, no?
It would, yeah, it would get very, very large and negative, right? I mean, it would go to minus infinity, I think. Right? Huh. What happens over here as t goes to infinity? B and M are constants, we're looking at e to the minus infinity, right? E to the minus infinity, otherwise known as 0, right? There's no mathematicians here. I'm allowed to write this. E to the minus infinity equals to 0. Okay? I mean, this, of course, is shorthand for a limiting process, blah, blah, blah. Slap my hand. Okay. Anyway, so v goes to 0. What? But v goes to minus infinity, but v goes to 0. I mean, these is two different limits, right? I mean, limit t goes to infinity, limit as x goes to infinity. One of these limits is physically reasonable. The other one is not. Because x doesn't go to infinity, as it happens. See what happens to x? What happens as t goes to infinity? What happens to x, actually? This goes away, and we get x naught plus m v naught over b. So it's a funny thing, right? It never stops, right? The velocity is never 0, and yet you start at position x naught, right? And then you approach this x naught plus m v naught over b position, right? But you never get there. So x never goes to infinity. So that limit over there is not physically reasonable, and that's why it seems to contradict the other thing, because it's not even a reasonable limit to look at. So limiting, yeah, be careful with limits, right? I mean, but this makes sense. Velocity goes to 0 as time goes to infinity. It never actually gets to actual 0, right? But as time goes to infinity, it gets closer and closer and closer and closer to this point, but it never actually gets to that point either. The motion's always bounded between x naught and x naught plus m v naught over b for this problem. It's an interesting question to see what happens when you trade this v for like square root of v or something else, right? And see these limiting questions, what happens in those other cases. I don't have the general story to tell you. I'm just saying it's something you could investigate, yeah? All right. Any questions? Would you like me to show you another VD-VDX trick? Here's one people always ask me when I worked at the Physics Tutorial Center at NC State when I was an undergraduate. It was the late 90s. They paid us $9 an hour. That's pretty nice, right? And half the time there wouldn't be people there. So I just play Quake with my friends Paul and Crazy Paul. And then people come in and say, hey, do my homework for me. And then I would usually waste 10 minutes of their time doing the following. I'll show you. I wish we had some physical space like this. It is a dedicated room with tables where you could go do physics and math and talk to graduate students. It's not going to work here. You could talk to undergraduates also in physics and math. Well, not math, but it's just Physics Tutorial Center, actually. But you go do your homework, and it was a great place. We have no place like that here. It's unfortunate. Let's see here. We do have a bowling alley in this building. It's kind of cool. I should start having office hours down there, you know? Oh, so here's a more known problem for you guys, right? How about MA equals to minus G? So I guess we'll trade our X for Y, so it looks a little bit more familiar. In other words, right, M d squared Y dt squared, right, equals to minus G. Of course, this is the net force equals to, oh, and I'm missing an M, aren't I? There we go. Don't tell Newton. He's dead. Anyway, so F equals minus mg, right? This is gravity, surface of the Earth, constant, right? So if I do dy dt, dv, dy, let me trade this back for dv dt, yeah? Okay. So dy dt, dv dy equals to minus mg. That gives me m v dv dy equals to minus mg. Of course, at some point we should cancel these m's because, after all, unless you're making a commercial for a water park or some kind of, I mean, for some reason, for comedic reason, fat people still slide faster down slides, but in reality, it's not the case. Well, I guess there could be some sort of weight dependence on friction or something, right? But allegedly,